Hello, everybody. Today we're doing chapter 3, question number 4 in Landau Lifshitz mechanics. Now, this question is going to be a little bit more exciting and interesting than the last few that we've done. We're going to be actually integrating some equations of motion, in this case, for a spherical pendulum. That means a pendulum that's free to swing in any direction. So I'm going to start drawing it here. Standard pendulum with a mass m at the end and a length of L, suspended from a pivot point above. And we're going to choose two variables, phi, that captures how high the pendulum is swung, and another angle, theta, that captures where the pendulum is around the vertical axis. Now with these variables, we can write our Lagrangian for the system, which is just kinetic energy plus the negative potential energy. And here we can calculate what the velocity is using our phi and theta coordinate system. So this vector is the velocity in the r phi theta coordinate system itself, and its magnitude is easy to calculate. Now we've got some symmetry, so due to rotational symmetry around the vertical axis, we're going to have a conserved quantity. And that conserved quantity will be the angular momentum around that vertical axis. And we'll call this quantity mz for the angular momentum around the z-axis. And using this, we can rewrite our Lagrangian, removing its dependence on phi dot. Now our Lagrangian is going to look like it just depends on phi and phi dot. And later we'll refer to this additional 1 over sine squared of phi term as a part of an effective potential energy. Our next conserved quantity is energy. And in this case, we can go ahead and just write U effective. Now we can begin to solve for phi dot in terms of E, U effective, and the other constants. And now flipping phi, which is d phi over dt, over, flipping it over, we get dt is equal to the square root of these constants times E minus U effective to the negative 1/2 power times d phi. This allows us to integrate both sides of the equation to get t is equal to the integral E minus U effective to negative 1/2 power d phi times some constants. Next we have another equation to use. So this time we're using the equation for the conservation of angular momentum around the z-axis. We're going to use this in order to solve for d theta in terms of dt. Combining with this with what we used before, we now have d theta in terms of d phi, which we can go ahead and integrate in order to have an integral for theta in terms of phi. Now the bounds of this integral are going to be the minimum and maximum values of phi. And we'll see what that means in just a moment. Phi determines how high the pendulum has swung, and so it's bounded by the energy. So the energy is equal to U effective when the pendulum is at the boundary. So this means that the pendulum can't go higher than a certain position, and it also cannot go lower than a certain position because the U effective, the effective potential energy, increases rapidly as the pendulum moves towards the bottom. So in this diagram, I'm indicating the two boundaries in red and next in blue. So the red boundary is the top, the blue boundary is the bottom, and the shaded region between is all of the positions that are possible for this pendulum given a certain energy. And the path that the pendulum takes will oscillate up and down between these two boundaries, like so.